The title of my talk is Red Giants, White Teeth, and the largest radio telescope of the world. And I hope in the next half hour, maybe 40 minutes, I'll be able to explain to you why there's a connection between these maybe not intuitively connected items. But basically what I'm going to try to tell you a little bit in this presentation is what astronomers are and what they do. And basically we try to answer two fundamental questions, and that is, how do we understand the world around us that we see? And where does all this stuff come from? So an example I'd like to give in this connection is that we all hopefully brush our teeth twice a day, and we buy toothpaste, maybe Colgate or any other brand, but most of the toothpaste that you'll get at ICA will have fluorine in it, because that's what makes our teeth healthy. And we just take this for a given, but where does the fluorine come from? Why do we even have fluorine that we can put into the toothpaste? Because none of it gets actually created on Earth. Earth has the fluorine that it has. And then how is that actually connected to red giant stars and radio telescopes? So let's see if I manage to explain this to you and convince you of this story. I've usually given this lecture for people who are significantly older than I think most of you. But you should definitely remember this picture and the table of elements. And I actually don't remember the exact number, but we have a whole bunch of elements that describe the physical world that we look at. And they go from the lightest element, hydrogen, to very heavy elements. But actually, when the universe was created, all we had after the Big Bang was a whole bunch of hydrogen, tiny amounts of helium, and even fewer amounts of lithium. Everything else got created during the evolution of the universe. And in order to understand how all those elements get created, we have to look at the life cycle of a star and how material is recycled in a cosmic sort of recycling factory. And we'll go from, oh, I don't have a laser pointing. Oh, wait. I'm pointing at my screen. I'll try to describe what it is I'm pointing at. We have to go from gigantic clouds and galaxies that contain molecular gas and dust, like we see here on the left. And out of these clouds, we form stars, which is the picture on the top. And around these stars, we form planetary systems. Eventually, these stars, they will die and they'll blow most of their mass into space, which we see here on the bottom right. And this material will move into space between the stars, which we see here in the Planetary Nebula on the bottom picture, and eventually get collected in new clouds of dust and gas where new stars were formed. So we have this sort of cycle of matter in the universe. I'm also going to try to actually remember to point out which of the pictures I'm showing are actual, real astronomical observations, and some of them are just artist impressions or animations. So in this slide here, the molecular cloud to the left and the two old stars here on the right bottom and middle bottom, those are actual images, and the others are animations, the other two. So how do stars form? So here we see another image. This is also an actual image on the top left of a part of a gigantic cloud of dust and gas. And you can see that some of these regions here, they have these little fingers sticking out. And these are actually regions where there's a denser part of the cloud that protects the cloud behind it from radiation that comes from bright stars around it. So they form like these little funnel of fingers. But these denser regions, at some point, the density in these regions is so high that the cloud will start to collapse under its own gravity. So you have a dense region with a little bit higher gravity than the area around it, so it will attract dust and gas that falls onto this region, which will make it more dense, which will increase the gravity and attract even more material. And this goes on. And if this goes fast enough, at some point, we call it a collapse of this dense region. But the material that falls into this dense region because of gravity, it doesn't fall straight onto the region. For physical reasons, this material, if the cloud is just rotating a very tiny little bit or moving a very tiny little bit, the material will actually start rotating and fall onto a disk that rotates around the forming star. And then it will first fall onto the disk, and then it will continue spiraling inwards and then fall onto the central region. And as more and more material collects in the central region, the density increases and the temperature increases. And at some point, it gets high enough for nuclear fusion to happen. And then this inner part will start glowing, and we call this a star. That's when we call it a star. So you have a star forming with a disk around it, and here in the bottom right you see an artist's impression of what that might look like. So once nuclear fusion sets in, you have a star very much like our sun. So this happened to our sun some 5 billion years ago. And if you look into the sun, what we have is basically a gigantic sphere of hydrogen. So if you remember, especially the first generation of stars, basically the universe only had hydrogen and a little bit of helium maybe. But in the core of this globe or this sphere of gas, the density and temperatures are high enough for hydrogen to fuse into helium. And what actually happens in this process is that you have two hydrogen atoms that collide. They shoot off a neutron and a neutrino, and sort of form this this red-gray intermediate thing, which then collides with another proton hydrogen atom to fuse together to this next thing. And when that happens, actually light radiation gets sent out. And this can happen twice. And when these two protons and neutrons hit together, they will fuse to form helium and shoot off two protons. And the density in the center of the sun is high enough for this actually to happen often enough. And all the radiation that you see from the sun today comes out of this process where I've indicated radiation here. So the star then starts shining, and actually at some point the brightness of the star becomes enough to stop matter from accreting onto the star. So you have some leftover material that still rotates in a disk around the star. And in this disk, in a relatively similar fashion, you will start building a planetary system. So maybe you guys already know this, but if you ever thought about it, the reason why all our planets around the sun are in one plane and they go around the sun in the same direction is because they formed in such a disk. But the point to remember here is that the material that the planets form from are from the material that originally was in the molecular cloud and that collapsed to start forming also the star. So the sun is actually in a very boring part of its evolution because it's going to go on doing this for another about 5 billion years. It will keep burning hydrogen into helium in its core. And initially, the temperature and the density is not high enough for anything to happen with helium. So in about 5 billion years, all the hydrogen will have been turned into helium in the core, and you'll have sort of a core of helium that's not doing much and an envelope of hydrogen around it. You'll have a small shell of hydrogen just outside of the helium core that is still hot enough to burn hydrogen into helium. But when this happens, it means that the energy production of the sun changes. And whenever something like that happens in a star, it has to restructure in order to sort of counterbalance this energy production. And what will happen with the sun is that it's going to blow up and become very, very big. That's why it will be called a giant. But if it gets this big, its surface temperature will go down, which makes the star look redder. So it will become a red giant. And actually, the size of the star of the sun is going to become about the same as the distance from Earth to the sun today. So it will be very massively bigger. So this shell of hydrogen burning into helium around the core, it will continuously dump helium onto the core. And at some point, the density and temperature, again, is going to be high enough for helium to fuse into carbon and oxygen. And this is through this process, you have two helium atoms colliding with each other. They form a beryllium atom. But Actually, beryllium is very short-lived. It will decay pretty quickly. However, the density is high enough for this to then collide with another helium atom, which then forms carbon. And if you go on with this, you can also form oxygen. So we formed, from hydrogen, we formed a little bit of helium, we formed helium, we formed a tiny bit of beryllium maybe, and carbon and oxygen. But where does the rest come from? And this is where Agb stars come in. And you might notice for the rest of the presentation that I'm really interested in Agb stars. That's my main research area, so this is what I'll be talking about. So Agb is a sort of a boring title. It stands for asymptotic giant branch star, and that's because in some diagrams where we sort of show where different types of stars are, we have one area where all the giants, they follow sort of a line like this in the diagram that goes straight from the bottom to the top. And then you have another class of stars, which are the Agb stars, that sort of lie sort of parallel to that line, but go a little bit higher. So they're sort of asymptotic to these giant branch stars. It's a very boring title, and for decades now we've been trying to come up with a more exciting name for Agb stars. But they're really cool. So on an Agb star, you have a core of carbon and oxygen, and the temperature and density never gets high enough for anything more to happen with these. But outside of these core, you have a shell where helium is still being burnt into carbon and oxygen. And outside of this shell, you have the hydrogen shell that still burns into helium. And then you have an envelope, where that's just hydrogen. It doesn't do very much. Now, for most of the time on for an Agb star, this just happens very quietly, and nothing really interesting happens. But every like 10 to 20,000 years or so, the helium burning to carbon and oxygen happens really, really rapidly, explosively. Several thousand times more energy gets released than during the more quiet phase. And this sudden release of energy causes the star to restructure again. So these shells, these two burning shells, they move outwards. And this period of really rapid burning only lasts for about 200 or 300 years, after which it turns off, so the shells move in. So you get these two burning shells that sort of move in and out every 10,000 years, and they have different regions mixing. So you're mixing protons and neutrons and electrons into different regions, which causes all this sort of really interesting chemistry and nucleosynthesis to create all kinds of new elements. So this is just a list of a few elements that get created in this process. And then after this rapid burning, the hydrogen envelope actually is not just sitting still, but it's sort of like a bubbling pot of water. So it sort of will mix all these new elements to the surface of the star. And the surface of the star is also moving in and out on a much shorter time scale than these 10,000 years, but with like a year or two, the surface of the star gets bigger and smaller and bigger and smaller. And as these new elements, this gas with new elements, it gets pushed outwards when the star gets bigger, and the star then gets smaller again. Some of the stuff stays out in the upper atmosphere of the star, where it can cool down, and then it will first stick together to form molecules like carbon monoxide or water or SiO, and lots of other molecules. And these then get pushed out further from the star, where at some point they get cold enough to stick together to form what we call dust grains. And these are micron-sized particles. And they're opaque to the light of the star. So they will absorb the light of the star, which will push them away from the star, and they'll collide with the gas that is still there and drag it along. So this actually causes the star to be stripped of gas over a few million years. It's going to blow almost all of its mass away into space. Or it's first going to build up like this big, gigantic envelope of dust and gas. And this is an image of one of those Agb stars. And the actual star you can't see because it's so hidden behind its cloud or its envelope of dust and gas. It's somewhere here in the center. This bright thing is not the star. It's just a bright part of the envelope. So this is a gigantic cloud of expanding dust and gas. And this is an actual picture. And this is also an actual picture. And here you can see these layers of dust and gas from the star that were blowing away. They form eventually a planetary nebula. And only the core of the star is still left over, and that core is so hot that it will illuminate the material that's moving away. And this material then eventually gets blown into the space between the stars, where it will collect in new molecular clouds, and now it will contain all those new elements that were formed inside the star. And then in those new molecular clouds, new stars will form with new planetary systems. And so this new planetary system will be formed out of material that contains all kinds of new elements. And that's how we get the fluorine onto Earth and eventually into our toothpaste. So now you might ask, how do we know this? Ideally, what we would want to do is, of course, go to all these new formed stars, sit there for a while and watch it form and measure everything we can measure and take samples of the gas and the dust. But first of all, they're very far away. And second of all, for the sun, it will take about 10 billion years to go through this evolution. So it's really difficult for one astronomer to do this. So what we do is we use telescopes to observe lots of different stars in different parts of the evolution, and then we sort of try to piece this together into one sequence. And we use basic physics to sort of describe how the elements are formed inside these stars and how the stars evolve. And then we use basic physics to make predictions of what we would expect to observe if we look at a star in a particular way with a telescope, and then we use observations to either confirm or reject these theories. And sort of this cycle of observations and basic physics is how we sort of step by step get closer to what we think is happening inside these stars. Now, there are a few things you need to know about astronomical observations, and that is that it very much matters what kind of size of telescope you have. So if we have a small telescope, we have what we call a large field of view. And this means that you can see a lot of the sky in one go. However, at very low resolution, you won't see a lot of detail. Everything will be a little bit blurred. If you have a large telescope, you have a relatively small field of view. So you will see a small part of the sky at one time, but you'll see it at very high resolution. Another thing that we have to think about is what wavelength we're looking at. So we have very short wavelengths, which is, for example, optical light. It's at about, and what you see down here, it's at about 500 nanometers. And this is, for example, what we see with the naked eye, or what the Hubble Space Telescope will observe. Then we have infrared light, which we normally experience as heat, but which is at much longer wavelengths. For example, here, 0.16 millimeters. And then we have radio observations. Here's an example of 0.85 millimeters. And now the image on the left this is a fake image. It's the cover of my PhD thesis, and my brother actually did this for me. But it's based on real data from the Hubble Space Telescope. And the infrared image here in the middle is of the same object. So in principle, we're looking at the same thing. However, just because the wavelength is so much longer, it just becomes a lot blobbier. And then if you go to radio, it's even worse. It's just some kind of misshapen, weird blob. And this is entirely because of different wavelengths. Another thing that astronomers look at, actually, is not just images, but we look at molecules and how molecules emit, because this tells us a lot of interesting details of the object we're looking at. So this is an example of a CO molecule. And this molecule won't just sit still in space. It actually vibrates. So this bond between the carbon and the oxygen atom gets stretched out and pulled together. So they vibrate like this, and they rotate. And when a molecule does this, it sends out light that we can detect with our radio telescope. And then we don't get pretty images usually, but we get this spectral line. And this is interesting because the intensity, so the height of the spectral line, will tell us how much of the molecule we have. So we can measure the mass, the total mass of gas that we're looking at. And the width tells us how fast this gas is moving. And this is interesting in order to measure, for example, rotation or the speed with which a star is losing its mass and things like that. The problem, however, is that, for example, one vibration rotation state of carbon monoxide has a wavelength of 2.6 millimeters. And this is 5,000 times longer than optical light. So the Hubble Space Telescope is 2.4 meters in diameter. And you remember, if I have a long wave, and it observes in the optical, and if I have a long wavelength, my resolution will get worse, which I can counteract by having a larger telescope. But in order to have the same resolution for the CO light emitted as I would have in an optical image with the Hubble Space Telescope, I'd have to have a 12-kilometer large telescope that can observe at 2.6 millimeters. And that's pretty big. So if we take just a map of Gothenburg and imagine we're going to build a 12-kilometer telescope, it would take about this size. And, well, I very much like Gothenburg, and I don't think it would be very nice for us if we would all live under a gigantic telescope. There's not a lot of sun in Sweden, but there's enough for me to not want to hide under a telescope. Fortunately, there's a trick in what we can do, and that's called interferometry. I won't go into the technical details, I'll just qualitatively describe what happens. So in interferometry, you can take one telescope, and you can take another telescope, and if you observe the same object on the sky at the same time, you can connect those two signals together. And actually, you will simulate a telescope that has the diameter that is equals to the distance of these two telescopes. And the cool thing with interferometry is you can add a third telescope and connect it with the other two, and you will simulate a telescope that has a diameter that equals the largest distance between any of these two telescopes. And you can go on and add a fourth telescope. And this is where ALMA comes in. ALMA is currently the largest radio telescope in the world, and it is an interferometry. So here you see one of the telescopes that ALMA has, and each telescope at ALMA itself is a 12-meter telescope. So the diameter of this telescope is 12 meters. And what people with ALMA did when they designed ALMA was they said, I'll take one of these 12-meter telescopes, and I'll take another one, and I'll take another one, and another one, and another one. And for some reason, some government gave the ALMA consortium so much money that they figured they would just keep designing and placing telescopes. And they placed them around like this. And they went on and on and on. There was a lot of money invested in ALMA. And actually they placed the telescope so that the largest distance between two telescopes is 16 kilometers. So this basically simulates a telescope that has a diameter of 16 kilometers. Now they built this telescope in the Atacama Desert in northern Chile at an altitude of 5,000 meters. And we put the telescope so high because we're above most of the atmosphere of Earth. And that allows us to make much more sensitive observations. ALMA consists of 54 telescopes with a 12-meter diameter, and then there are also 12 telescopes with a 7-meter diameter. Because for some observations, we actually want these telescopes to also stand very close, and they need to stand so close to each other that the 12-meter diameter telescopes will bump into each other. So this is where ALMA is built. It's operated by an operation support facility that is actually only at 3,000 meters. And then the telescope itself is a little bit further away at 5,000 meters. So this is the support facility where you see the buildings for all the astronomers and technicians where they can live, and maintenance areas for the telescopes. And this is on the top site where the telescope stands. Here in the bottom, you can actually see a few of the antennas standing around. And then you see the roads that go out to where all the other antennas are. And the ALMA correlator, this is the building where all the signals of the antennas get combined to simulate your big telescope. And this building actually has two floors. It has the bottom floor with the computers for combining the signal, and then the entire top floor is an air conditioning. It's the largest air conditioning unit in the southern hemisphere, and that's of course needed to cool the computers. So it's actually difficult to get a picture of all of ALMA because the telescope is so big that if you would make a picture that's wide enough to see all the antennas, each antenna will be tiny. So here you see a group of antennas in the center, and here you also see a few more antennas. It's really cool. It's very exhausting to be up on 5,000 meters, but it's an amazing sight to witness. And here are some more antennas. It looks like they're all pointing in different directions, but it's not. It's just because it's one of those panorama views that will give you the feeling that they're looking in different directions. So what does ALMA do for us? So this is an image of a star-forming cloud, similar to the images that we saw earlier. And before ALMA, this was the sharpest image we had of this region. But then ALMA came along and we observed it. And this is what it looked like when we looked at it with ALMA. So you can see all these sort of blobs, they break up into really small detail. And all of these little dots here are areas where new stars are forming. And as I explained before, when this new star forms, they form in the center and then they have a rotating disk. Another thing that ALMA actually has done is taken an image of such a planet-forming disk. So in this image, in the center, in the brighter spots, there will be a star. And then you can see this disk of dust moving around the star. And you see these gaps. Now, these gaps are not directly caused by planets, but they are the signature of planets forming inside this disk. So we are now with ALMA actually observing the process of planet formation. And what has ALMA done for Agb stars? So like I said before, we have this process where we have this rapid helium burning. First. So the star blows away its stuff and makes this big shell of dust and gas. And we can use ALMA to observe these envelopes. And what we do there is a spectroscopy. So this is a spectrum taken with ALMA of one of these envelopes. And you can see there are all these signatures for molecules. And we have some identified, like we have HCN mainly in this spectrum, but we have a lot of these U's, and U in astronomy speak stands for unidentified line. So with ALMA, because we have so many telescopes that are observing at the same time, these are the most sensitive observations that we've ever had. And we're actually discovering a lot of unknown molecules. So these observations give us really new information about the chemical processes inside the stars, because all these molecules are created through elements that were created inside the stars. So we can now determine how much of what molecule is formed in what kind of star. But, sorry, I have to see it. Okay. So, but I was saying that all these elements, they get created when this rapid helium burning happens and the star restructures, and this goes on for a few 200 years. And then these shells, they move around and you get all these new elements. And what happens during this 200-year period is that the rate at which the star loses its mass increases a lot, just for about 200 years, and then it decreases again. So here we're going to see a film, and it takes a few seconds, but you can see this is a model of a star losing mass, and you can see how just during the regular period, it is building up this envelope of dust and gas. But what happens at T0 is that we have this short period of rapid burning where the mass loss goes up. And for 200 years, you get this explosive mass loss, which actually creates a wind that runs into the previous wind, and it creates this thin shell of dust and gas moving outwards. In this particular case, we're also simulating not a star that is alone, but a star that has a binary companion, and that forms the wind into this spiral shape. But we expected to see these thin shells of dust and gas that you see here because of this process of where new elements are being formed inside the star. And some of the very first observations with ALMA produced this image here on the right. And amazingly, we saw this thin shell of dust and gas. And we also saw this spiral structure, or signs of the spiral structure, due to this binary companion. So this was really exciting stuff. This was when ALMA only had 11 antennas or telescopes and not the 54. So this gave us unique details. And it actually allowed us to measure how much the mass loss increases during this short period of helium burning. And how the mass loss has changed afterwards. So we can actually now directly measure how much dust and gas this star blows into space. And this will then, eventually this star will form a planetary nebula, and that material will get put into the interstellar medium, where it forms new clouds and it can form new stars and planets. So we're sort of figuring out what kind of material the stars are formed of, and also how the planets are formed out of the remaining gas and dust and out of this material. And the special thing about ALMA is that for the first time we can actually observe all the stages of the evolution of stars and the universe. We can look at the details of the clouds, we can watch the star or can see images of the star and the planets forming, and we can look at what happens when the star dies and loses all its mass, giving us all this information that we need to know to understand where everything comes from. And if you don't take away anything else from this lecture or this presentation, I want you to think about this. What this means, when the universe was formed, it only had hydrogen, a little bit of helium and lithium. And this means that everything that we see, almost everything that we see around us, all the matter that builds our bodies or the furniture around us or whatever, all of those atoms were created inside of stars at some point in the universe, and then became part of our world 5 billion years ago when the sun and the earth were formed. Just think about that. We are truly stardust. Oh, I'm sorry, I'll just leave it out there because that was the end of my presentation. I thought I had another slide, but never mind. Well, maybe I'll leave the presentation because it might be nicer to see some people.
Yeah, but thank you so much for this lecture, and I think we have time for some questions. So if you have any questions, just leave them in the chat or unmute yourself. So I think we have a question.
Yeah, so the question is, I don't know if everyone's reading the chat. So I said that in ALMA, some of the telescopes are 7 meters instead of 12 because we want them to stand close. That's true. So the tricky thing so interferometry is really cool because if you place 2 telescopes far away, they simulate a telescope of that diameter. So, but that's only half of the story. The problem is, basically what you're doing by placing a lot of telescopes is you're simulating your big telescope, and you're bit by bit filling in the surface of that actual telescope. So ideally, you would have so many telescopes that fill the entire surface of your big telescope. By not filling that entire surface, you're missing some information. And you can think of it as on any given telescope, the diameter will tell you how much small detail you can see. But the inner parts, so the parts that are close together, they will show you how much big structures you can see. So if your telescopes are too far apart, you can see very small details. But if you have something that is sort of big and extended, it will filter out. And it's difficult to explain the technical background to that, but basically you won't see it. If you have a very smooth, large emission, you won't see this. So you want to have both telescopes that are very far apart, but also some that are very close together. So actually what ALMA does is it has the 12-meter telescopes that stand relatively far apart. Then it has 7-meter telescopes that can stand pretty close. But it also has 4 telescopes that just observe as a single telescope, because that will give you the most extended emission. So we get all scales together. I hope that answered the question. So yeah, so this is similar to so there are 2 reasons why you want to have a lot of telescopes. First of all, the more telescopes you have, the larger the collecting area you have. So a telescope just collects photons that hit it. And if I have 2 12-meter telescopes, a certain number of photons will hit the telescopes. If I have 10 times as many telescopes, I will be able to collect 10 times as many photons, so I get more sensitive. So that's the one reason why you want to have many telescopes. But the other reason why you want to have is sort of similar to the question we had before. If I have these 2 telescopes, they will be able to see the detail of that emission, but they will relatively quickly start filtering out any emission that is bigger. So by having actually a large number of telescopes, you get a wider range of scales at a larger sensitivity. And actually the telescopes are not even placed in random places. They have a very specific pattern so that as the Earth rotates under the sky, the projected distance between telescopes changes. So you get even a wider range of distances between the different telescopes. Agb, it's not a dumb question. Like I said, it's a very boring name and it's not intuitive. Agb stands for asymptotic giant branch, and this is simply because of what it looks like if we plot stars of different types in a diagram that's called the Hertzsprung-Russell diagram. Agb stars will lie in a certain part of that diagram, which is sort of parallel to the line of where giant stars will lie, and that's why they got the name asymptotic giants. And we have to come up with a more exciting name. Yes, this is a very good question. It has to do with optics. That's my simple answer. If you draw the light path and see how a telescope magnifies things, you can derive what the field of view is. The cool thing and the resolution. And then you'll see that that the field of view goes as the wavelength over the diameter of the telescope. So if you have a large diameter, your field of view will go down. The cool thing with interferometry is that the field of view actually will be that of one of the single telescopes. So the field of view for ALMA is that of a 12-meter telescope, but your resolution will be that of the largest distance between two telescopes. So in ALMA, you get it both. You get a telescope with a relatively large field of view and a high resolution. But to explain the exact details of that, one would have to write down the equations of interferometry, and that is magic to me. So the planetary nebula, so the question is, how do planetary nebulae form? So you have the evolved star that loses most of its mass, and it just blows all this gas away from its surface. Actually, it will almost lose all of its mass this way. But at some point, this process stops. So the star will stop losing mass, and only the core of the star will be left. But this material that was blown away, it keeps moving away to further and further distances from the star. So this envelope detaches from the star. But the core is super hot, and that radiation is hot enough to ionize this gas. And when the gas gets ionized, we can observe it in the optical. So it sort of lights up and becomes this, what we call a planetary nebula. The name planetary nebula is a little bit misleading because it has absolutely nothing to do with the planets. The reason why it's called a planetary nebula is because long before we knew, not long before we had big and sensitive telescopes, the first astronomers, they observed these objects and they looked like planets to them. And it's only much, much later that we figured out that these were dying stars, or the remnants of dying stars, actually. But astronomers have a tendency, we were very traditional people, so we stick to the original names, although they shouldn't be. So they have nothing to do with planets.
And yeah, I also want to thank you for this lecture and that you were willing to do this. And yeah, as you can see, it was very appreciated.